All right, so on to problem 4. This is the fourth problem in the series, so I've mixed it up a little bit, combined some other topics that you've learned. I made a small annotation. If you're in my class and you downloaded these problems to work on them, that change should have been incorporated there. It's not the only way that you know that this is liquid butane, though. So we've got our lighter. It's got 1.745 milliliters of liquid butane. Also, in our chemical reaction, right, our state symbol says, hey, this is a liquid. That's important. That means we can't use gas laws for this 1.745 milliliters. If you did, maybe you should go back and retry the problem with that in mind. Another hint that that's a liquid is the fact that we have density here, and so we're not going to be using gas laws for that part. Now, if all of that butane was burned, how many liters of oxygen would be consumed at STP? So we're looking for liters of oxygen, and we're at STP again to make things a little bit easier. So remember, that's 273.15 Kelvin and 1 atmosphere. And that lets us use 22.41 liters per mole. And again, this is a stoichiometry problem because we have butane, we're looking for oxygen. Those are two different chemical compounds. We're given a balanced chemical equation, though, that gives us the relationship between butane burned and oxygen consumed. So we can't calculate, at least off the bat, how many moles of oxygen there are, but again, this is moles of A, essentially, moles of butane, convert to moles of oxygen, which means I need to find the moles of butane first. Now, I was given density, 1.745 milliliters C4H10. That density is important because look, that density lets me convert between milliliters and grams. So I have milliliters of butane right now, but I know that if I get to grams of butane, I can use molar mass of butane to calculate the moles. So to get to grams first, I have to use my density. Now, anytime you see units written like this, it's 0.8000 grams per 1 milliliter. So whatever that's after the slash, that's per 1 of whatever comes after the slash. So here, in my stoichiometry, my actual calculation now, I have milliliters. So I want to put 1 milliliter on the bottom and the 0.8000 grams on top. And I want to keep all of my sig figs, excuse me. Okay, so now C4H10, I need my molar mass. So we're going to multiply by 12.01 and by 1.01. And these molar masses on your calculator, you can do them this way. So 4 times 12.01 plus 10 times 1.01. Give it a shot, try it out, compare it to the way that you normally calculate it, and it should give you the same thing. So that's grams per mole. And I'm trying to convert now from my grams to moles of butane. All right, so we want to keep that part of the units. We want to keep the fact that it's grams in there, or sorry, the fact that it's butane in there, so we don't forget where we're at and where we're going and what units we need to cancel. So C4H10, I need now my mole ratio because I've calculated the number of moles after this step. The mole ratio between butane and oxygen. It's a pretty big ratio. For every 2 moles of C4H10, I need to consume 26 moles of O2. And again, if you got to this point and you converted to grams, you have to think about why you're doing the next step. This is why you can't just memorize steps, because we don't want grams of oxygen. We want liters of oxygen. And again, we can look back to the fact that we're at STP and use 22.41 liters per mole. So I have 1 mole on the bottom because I want to cancel out moles, so 22.41 liters on top. And once we calculate this out, that should give us the final answer. So 1.745 times 0.8 times 26 times 22.41 divided by 58.14 divided by 2. And that gives me 6.995 liters of oxygen. Now, sig figs, looks like we have 4. So with correct sig figs, this will be 6.995 liters of oxygen. Give that away so you can pause, and I'll move on to the next.